Hey everyone, we're going to take a minute here to look at one other thing that we can do with energy interaction. Specifically, we're going to look at how we can apply energy interaction to chemical reactions. Now, there is going to be a decent amount of stuff in this video that comes from chemistry. If you're not sure on some of this stuff, I encourage you to bring it to an office hour and ask an instructor about it. We're more than happy to help. Let's look at a chemical equation. A chemical equation just describes how a particular reaction takes place. This chemical equation describes the combustion of propane. Propane is a kind of fuel that's used for a bunch of different things, like heating and cooking. Combustion just means to burn. What this equation says is that we have 1 mole of propane and 5 moles of oxygen, and they turn into 3 moles of carbon dioxide and 4 moles of water. A mole is just a number to describe how much of something that we have. When we're not dealing with chemical reactions, we'll usually measure amounts in kilograms. But here we're measuring them in moles. Let's say that we wanted to know what the change in energy was during this process. Let's start by just thinking about the problem and seeing if we have any intuition. Now, maybe you don't look at this and know off the top of your head whether the total amount of energy is staying the same or energy is going in or going out. But what is this? We're burning propane. And what happens when we burn something? Burning things produces a lot of heat. You've probably never thought about it, but this is just energy that's leaving the system. For example, if you have a gas fireplace, you're burning some sort of gas to produce heat to warm your home. That heat is leaving the system, that is the fireplace, and going out into the surrounding environment. So our intuition is telling us that the amount of energy in the system should be going down. In other words, once the chemical reaction takes place, the system should have less energy than it started with because that energy is leaving the system to perhaps warm your house. But let's see how we can describe this with an energy interaction diagram. Now, I'm going to claim that we've actually sort of already seen this. These changes are actually bond energy changes. These substances have bonds between them. For example, the carbon atoms and the hydrogen atoms in the propane are bonded together, as are the oxygen atoms. In a sense, these bonds are being reconfigured. Some bonds are being broken and new ones are being formed so that once the process is done, we now have carbon dioxide and water. The way that we describe this with an energy interaction diagram is by drawing a bubble for each substance in the process. In this case, there are just 4 substances, so we need 4 bubbles. Let's now label the bubbles by which substance they're for. Now, as I sort of said, these energy changes are bond energy changes. Bonds between some substances are being broken while new bonds are being formed. The question, though, is which direction these bond energy changes are going. Let's start with the substances on the left-hand side of the equation. These are the things that we start with, the propane and the oxygen. Now, we're going to think about chemical reactions in a very particular way. We're just going to think of a chemical reaction as a sort of reassembling of the products. We're going to say that we take the things that we start with, in this case the propane and the oxygen, and pull them apart, breaking all the bonds between them. And we then reconfigure them into the stuff on the other side of the equation. Now, what happens when we break bonds? Well, we actually already know the answer to this. An example is when we boil water, letting it go from a liquid to a gas. We said that in this case, bond energy increases. So for a chemical equation like this, the reactants, the stuff on the left-hand side, always will have their bond energy increase. We're breaking the bonds between the individual atoms, causing the bond energy to increase. What about the stuff on the right-hand side? Well, you can probably guess. In this case, the bond energy is decreasing. Just as when we broke apart atoms on the left-hand side, bond energy increased, putting atoms back together and creating bonds causes bond energy to decrease. But remember, when we draw energy interaction diagrams, we also have to state more clearly how we know this is the case. In this case, we know that these things are happening because certain substances are disappearing. We start with a mole of propane and 5 moles of oxygen, and we end with no moles of propane and no moles of oxygen. Moles are represented by an N, so we know the bond energy of this substance is increasing because the number of moles of the substance is going down. Same with the oxygen. For the carbon dioxide and the water, it's the exact opposite. We know the bond energy is decreasing because the number of moles of these substances is going up. But we can even do better than this. This chemical equation tells us exactly how many moles we start and finish with, so we can include that in our energy interaction diagram. In general, the more information you can include in your energy interaction diagram, the better. We start with 1 mole of propane. If you don't see a number in front of a substance, then you know we just have 1 mole. We start with 1 mole, and we end with 0 moles. There's no propane on the right side. For the oxygen, we start with 5 moles. And again, we end with 0 moles because there is no oxygen on the right-hand side. For the carbon dioxide and the water, it's the exact opposite. We start with 0 moles of carbon dioxide and 0 moles of water because there's no carbon dioxide or water on the left-hand side of this reaction. We end with 3 moles of carbon dioxide and 4 moles of water. We're just reading these numbers off of the chemical equation. But our energy interaction diagram isn't done yet. We haven't indicated whether our system is open or closed, and we haven't written an equation. Let's start with the first one. Is this system open or closed? Well, I sort of already gave you the answer. Propane is used as a fuel source. If the energy that we got out of it wasn't allowed to go anywhere, it wouldn't be very useful to us. This is an open system. The energy that comes out during the reaction is being used to do something useful outside of our system. Do we care what that useful thing is? Not really. We're just interested in knowing that there's energy leaving the system. We represent this with a dotted line around the energy bubbles. We suspect that energy is leaving the system. The propane is producing energy that goes out into the environment to do something interesting. To represent that, we draw a little arrow pointing out of the system and label it Q. Now, a little aside, I did mention that there's 2 ways that energy can enter or leave the system, as heat or as work. For now, we're not going to worry about work, so if energy enters or leaves your system, you can assume that it's doing so through heat. The last thing we want to do is write an equation, so let's do that. Let's start with our very general energy conservation equation. It's exactly the same as for the previous example, just delta E total is equal to Q plus W. But unlike the previous example, Q and W are not necessarily 0. Now, I said we don't have to worry about work, so let's just say it's 0 and not worry about it. But Q is not 0, so it's going to have to stay in our equation. Now, let's expand this. We'll expand it just like we did in the previous example. We have 4 bubbles, so we need 4 terms in our equation. All of this is going to be equal to the heat that leaves our system. Now you're actually going to do this exact problem in DL, and you're going to go through and compute the exact amount of energy that comes out of this process. So I'm not going to do that whole thing here. But I do want to show you one more thing. We have these delta E bonds, but we don't necessarily know what the equation looks like. We did learn in the last video an equation for the change in bond energy when we're talking about phase changes, But what about chemical reactions? Well, interestingly enough, they pretty much look exactly the same, with a very slight difference. When we're dealing with changes in bond energy in chemical reactions, we write the change in bond energy like this. This looks very, very similar to the change in bond energy we saw for phase changes, with one key difference. Instead of a delta M here, we have a delta N. Remember, N is just the number of moles of a substance. So this equation functions the exact same way as the previous one. Delta N is just the amount of your substance that is changing, and then delta H is just the number that describes how much energy it takes to make that transition. One thing I want to note though, delta H is not the same when you're talking about moles as it is when you're talking about kilograms. Generally, when we're talking about phase changes, we will be measuring the amount of our substance in kilograms, and our delta H value will reflect this fact. But when we're dealing with chemical equations, we're now measuring our amount of substance in moles, and so delta H will be a different number. Regardless though, we'll always give you the number on an exam. You're never going to have to memorize it or guess. That's all for this video. I'll see you in the next one.